In this video, we'll do a classic example of a related rates problem using basically a ladder leaning against a wall. That's the classic example. So I'm going to start by drawing a diagram. There we go. And I need to clean this up a little bit. So, oops, not there. Here. Let's say we have a wall and a floor. Okay. And then we have a ladder leaning against the wall. Okay. And let's say that previously the ladder was like this, like leaning up real close, right? You know what? Actually, I'm sorry. There we go, much better. So originally the ladder was like leaning up against the wall, right? And then the bottom was being pulled out. So let's say we have a 10-foot ladder, okay? And the bottom is being pulled, let's say at a rate, let's say, I don't know, 2 feet per minute. So pretty slowly. Yeah, well, let's say per second, 2 feet per second. So pretty quick, okay? It's essentially falling down by someone pulling at the bottom. Now, the bottom doesn't go faster as it moves, just from start to finish, from fully parallel with the wall to fully parallel with the floor. That whole transition, the bottom of the ladder, the base of the ladder is moving at a constant rate of 2 feet per second. Okay. Now, the classic question then is, of course, the bottom is moving down, right? It's going to end up on the floor at the end. At what rate? At what rate is the top of the ladder moving? Because it's not 2 feet per second. And if you go and you probably don't use a ladder to do this, that'd be, risk damaging something. But if you got a yardstick, if you have a broom, if you have anything like that, you can go lean against the wall and pull the bottom out. If you watch the top initially drops quickly and then slowly at the end. So the top does not move at a constant rate, which maybe is surprising, maybe not. But then the question is, well, at what rate? So that's the statement of the problem, and this problem is typically you're not given an equation to deal with. Now, in this course, on the online homework and the exams, you'll be given an equation. Don't worry too much. So for this one, I'm just going to tell you, without going into maybe all the reasons why, maybe once I explain it, it will be pretty clear. I need to use the Pythagorean Theorem because I have a triangle here, right? I'm going to call the base of the triangle x and the altitude of the triangle y, just for convenience, x and y. And then the hypotenuse of the triangle is the 10 feet that the ladder is made up of, right? So I can say that x, y, and 10 are related by x squared plus y squared equals 10 squared, right? Pythagorean theorem. In a sort of a calculus course for scientists and engineers, they would be expected to figure that out. You should know that already, right? You should know how to try to approach this kind of problem. But for this class, you're not engineering students, so we'll make things a little bit easier in the sense that you're generally given the equation to start with. Okay, so what I need to figure out, I have this equation. What I need to figure out is how to interpret these numbers. Which of these change over time, and which of them do not change over time? If you think about it, we hope that the length of the ladder does not change over time, right? You're not going to start cutting pieces off of it. And I've already told you that this number does not change over time, the 2 feet per second. But it may be pretty obvious that the x does change as a function of time, okay? And the y does change over time. And I actually left out a piece of information. We need to ask, at what rate is this moving at a certain point in time? I need to specify when, because it changes over time. It's not constant, as I said earlier. So when, let's say when x equals 4, when the base of the ladder is 4 feet from the wall, how quickly is the top of the ladder moving? Okay. Now, in the previous example, we knew we were doing related rates, so we applied a time derivative to both sides of the equation. So that's what I'll do here. I'll say that I want to find d dt of both sides of the equation. There are several steps in this kind of problem, and for some of the steps, the order is optional, which order you want to do things in. So there's actually something we haven't done yet that we could have done already, but that's fine. We don't need to necessarily do things in the most efficient order every time. I think it's important just to see the overall process of how do you solve this problem. So now, when I find the derivative with respect to time of x squared, remember x is not the variable with respect to which the derivative is being applied. The derivative is being applied with respect to t, not x. So in previous examples on implicit differentiation, we would find the derivative with respect to x of like y squared, for example. And we'd have to use the chain rule because x and y are different variables. That's the situation we have here. We're not using x as the variable for the derivative. So I have to apply the chain rule. So the derivative of x squared, I'll use the power rule, so 2x. But then I have to use the chain rule, dx dt plus, and again I use the chain rule here when I find the derivative of y squared with respect to time. So this will be 2y times dy dt equals, and this might be obvious, but perhaps not, the derivative of a number is always 0, regardless of the variable. 100 does not change when time changes, so this is 0. Okay. So this is an equation that relates not just the base and height of that triangle, or base and altitude of that triangle, but also the rates at which they are changing. Now we were given one of the rates, so pause the video and think for a second. Which rate is this 2 feet per second? Is it dx dt or dy dt? So maybe you've thought about it. This is dx dt. This is the rate at which the bottom is being moved or being pulled. So this is the rate at which x, being the distance from the base to the wall, changes. So I can say, in this part I could have done earlier, I could have said, okay, well, dx dt, that is equal to 2, okay? Because this length here, this distance is growing by 2 feet per second. The base is being pulled away from the wall. So that means this number can plug in there, okay? And this 4, when x is 4, that plugs in there. Now, ultimately, we are looking for dy dt. What is the rate at which the top is moving? Which is another thing we could have said earlier. So I can say, well, this is not really a question mark. I know that this is dy dt, and I just need to determine what number that is. So I've got a number for x, I've got a number for dx dt. I do not have a number for y. I need to find out a number for y. And that might not be very hard. It might be pretty clear to you, how do I get a number for y if I have a number for x? And so here's the important part. This is an important point at which to observe something. I should not plug in 4 too early. Before I apply the derivative, x is a variable that changes over time. So I need to find the derivative, and then later I can plug in 4. So here I can plug in 4 for x right here if I want. I should not plug in x too early, because then, well, the derivative of 16 is 0, and I won't get anywhere, okay? So you need to make sure to only plug in numbers for things that do not change, like this 10. 10 squared I went ahead and put at the beginning, because the ladder length doesn't change. But for both x and y, I can't put in those numbers yet. So how am I going to get a number for y? Well, again, I need to use Pythagorean Theorem because I have a right triangle here. So x squared plus y squared is 10 squared. When x is 4, that will allow me to get a number for y. So 4 squared plus y squared equals 10 squared. So 16 plus y squared equals 100. Trying not to let my y's look like 4s. This one kind of does, but hopefully in context we're okay. So y squared equals 84. So y, now y is always going to be positive, right? Because y is the altitude of that triangle. It can't be negative. So I don't have to worry about plus or minus here. This is the square root of 84. And if you want, that reduces to root 21, if you want to simplify it a little bit. Okay, so that's my y value. So now I can take this equation and bring it down here where I have more room. 2x times dx, dx dt, plus 2y times dy dt equals 0. So now I can plug in 4 for x, negative 2, positive 2, for dx dt, right? This is positive 2, plus 2 times 2 root 21 times dy dt equals 0. So I've plugged in all the numbers, either that I was given or that I worked out using the Pythagorean Theorem. So now I can solve for dy dt. the hard part is done, the calculus part is over. I'm just solving an equation now. So I'll subtract 16 on both sides. So 4 root 21, that 4 comes from combining the 2's to make 4, times dy dt equals negative 16. You might notice a way to be perhaps a little more efficient here. So if you do, that's awesome. I'm not worried about being as efficient as possible. Try to make this as clear as possible. So next I'll divide by 4 times root 21. So this will become dy dt equals negative 16 over 4 times root 21. And of course, 16 and 4 reduce, so dy dt is negative 4 over root 21. And this is in feet per second, right? Okay. This is another reason to use the Leibniz fractional notation, because the top will tell you, basically the derivative notation tells you what units to use. The dy is the change in y. Well, y is measured in feet. The dt, well, that's measured, that's a change in time, and time is measured in seconds, so feet per second. Sometimes we'll want a decimal approximation, so let's go ahead and do that for this one. You don't always need that, but let's go ahead and do it for this one just so we can get a more tangible number, because if you look at this, you might be unclear. Yeah, but how much is that? Is that a lot? So this is about negative 0.87 feet per second. Oops. Come on, 7 in feet per second. Okay, so not very quick. The bottom is being pulled at 2 feet per second, and at such a time when the bottom is currently 4 feet from the wall, so 2 seconds later, right, the top will be moving at almost 1 foot per second, but not quite. So anyway, that's that example. It's several steps, but that's the classic example of a related rates problem.